So having defined all these concepts, we can now talk about whether the interpretation satisfies the formula or model of a formula, um, equivalent, satisfiability, entailment. Note here that these definitions are pretty much similar to propositional logic definitions. Okay, so we say satisfaction between the we define satisfaction as a notion between the interpretation and the formula. Okay, so I satisfy a formula f if I is a model of f. Okay, um, so I is a model of f if the formula f under the evaluation I, under the interpretation I, returns true. Now note here that we're not going to say this for any formula, but for closed formula or sentence. Okay, so these notions are defined only when f has no free variables. Okay. The second definition is logical validity, and that means actually the same as tautology in propositional logic. If every interpretation satisfies the formula f. For historic reason, we don't usually say f is a tautology in the first order logic case, and instead we prefer to use logical validity, but they actually mean the same thing. Two sentences, or you can say even two sets of sentences, are equivalent if they are satisfied by the same interpretation. Okay. So sometimes you want to say a formula is logically valid. Well, of course, I said you cannot evaluate this formula, but you can make a universal closure. Okay, so you can say f and g, I'm sorry, a formula is logically valid, even if it has a free variable. Then if you refer to this universal clause, you can say that. So if a universal clause is logically valid, you can say a formula is logically valid. Okay. Similarly, f and g are equivalent if this formula that you see is logically valid. And like before, set of sentences satisfiable if you can find at least one interpretation satisfying all sentences in gamma. A set of gamma of sentences entails a formula f if every interpretation satisfying gamma satisfies the universal clause of f. So I want to emphasize the role of entailment here. So it's not a colloquial term. Okay, it's a precisely mathematically defined in terms of the relation between the set of sentences and a formula. Okay, and I said this is a very important notion in knowledge representation. So you represent knowledge in gamma, okay, or knowledge base. Gamma is a knowledge base, and f is when you say gamma entails f, means if an agent believes everything in the gamma, it has to believe also f. Okay, so f is a logical consequence of gamma. Okay, and that is defined as for each interpretation that satisfies gamma, it satisfies f as well. Okay. All right, so far so good. First of the logic is rich in terms of expressing objects and relations and functions. Now, some bad news. Okay. The validity problem of first order logic, okay, is actually undecidable. So that means you cannot find an algorithm to decide when you're given any sentence and check whether f is satisfied by every interpretation. Intuitively, it makes sense because how many interpretations can you define in the first order for the first order signature? If you go back to, let's say, this example, okay? So even for this simple case, I could have used a different universe to be a part of interpretation, okay? Okay, or I could have map A to be very different ways, or I could have map P to be in very different ways, okay? So you'll see actually there are infinitely many interpretations that you can define, even if you're given a finite signature. Okay, a formal proof involves a post-correspondence problem to be reduced to this validity problem. Okay, for those of you who are experienced in theory of computation, post-correspondence problem is an undecidable problem. So, in the textbook on a textbook on this theory of computation, the book that I actually use in my undergraduate course actually has this proof. Okay, so for this course, we are not going into this proof in detail, but basically this is actually a fundamental fact that we have to admit that first of the logic, it has very good representational power, but if we want to use it for computation, then we have no hope to decide it. Okay, now another bad news, corollary. So the satisfiability problem is also undecidable. So, okay, so this means given from sentence F, if is F satisfiable, it's undecidable. Okay, so it's not about all interpretation satisfying the formula, but even for finding a single interpretation that satisfies the formula is also undecidable. Well, the reason for that is actually you can reduce the validity problem to satisfiability problem, given the fact that F is logically valid if and only if not F is unsatisfiable. Okay, so why? Well, you can assume that F is logically valid. Okay, that means for all interpretation F is true, which means that if you negate it, then there's no interpretation that satisfies F. So logical validity of F is actually the same thing as unsatisfiability of not F. Okay. So if you can, of course, answer satisfiability problem, you can answer logical validity problem, but it's known to be undecidable. Okay. All right. So then we have to actually restrict first order logic in some meaningful way. And this is where actually many of AI researchers have begun. Because in McCarthy's original idea was to axiomatize this common sense reasoning problem of getting to the airport in terms of some logical formulas. And he was actually using first order logic formulas to sketch the idea. And it turns out that there are actually many problems. Okay, we will come across this later in this course. But one thing is actually we cannot decide the validity, or even the satisfiability. Okay, so in the next, we are going to talk about the semantic web languages where certain decidability is really crucial. Okay, so we'll actually study the subject. Even if there are infinitely many objects in the universe, there is a way to actually restrict the first order logic so that we can talk about this validity and satisfiability as a decidable way. Okay? So we can find an algorithm for that subset of the first order logic. Now, before we actually go into that, there's actually another way to restrict first order logic that works very similar to propositional logic. And this is by looking at some particular fragment of first order models, which are called Herbrand models. And for this one, it's actually detailed in the handout that I gave. The reading material is not actually very detailed, so I supplemented with this thing, and it will be actually useful also later in this course. So for this one, I will actually going to lecture in the class, okay, and we're going to do some exercise problems there. All right, one last thing. There will be homework, which is due on September 10th, 11:59 p.m. The submission instruction was already given in the syllabus. Be careful, we are going to use Blackboard and you have to type in. Okay, we are going to use plagiarism checker. Okay, because we have many students in class, it's not feasible for us or for TA to collect all the papers and manage this homework in an offline way. Okay, so be cautious on following these instructions. So in order to save the TA's time for really focusing on grading and use her hours of effectively, okay, to communicate with you, please follow these instructions carefully. Okay. All right. Thanks for thank you, and we'll see you in class.